Hey guys, it's Michael with Breaking Concepts today, and today we're going to take a look at one quick question about drug concentration, which we're going to use our knowledge of recursive sequence, difference equation. So without further ado, let's try and pause this video and try and attempt it yourself. Okay, just a quick note. I'm actually going to tell you my attempt originally, which was wrong, the mistake that I made and why I made the mistake. But right now, let's kind of go into the answer. So right off the bat from the question, right, suppose CT is the concentration of the drug in the bloodstream at time t, A is the concentration of drug that is administered at each time step, and K is the fraction of the drug metabolized. So let me just explain metabolize. So basically, you have a drug, and when it's metabolized, means that your body, you have already broken it down. And so K being the fraction of drug that is metabolized, meaning that K is the portion where the drug does not exist anymore. That's actually not what we're looking for. What we're looking for is this drug that's still within our system. So just a quick hint here at first. First of all, we want to make sure we know that K is the fraction which is metabolized. And we can't really use a metabolized fraction to solve this question because we want to know how much are still retained, which means how much drug that hasn't been metabolized. And the way we do it is actually pretty simple. We do 1 minus K, then we have the fraction of the drugs that has not, I'm going to make a big cross, has not been metabolized. That's still in the system. And so let me make a small diagram about what is actually going on. So let's say we have time equals to 1, right? T1, T2, and T3, T4. Okay, so A is the concentration that the drug is administered each time step. So what we have here is plus, I'm just going to move you at a plus A, plus A, plus A, plus A. So every time step, there's A, which is the concentration of drug that's administered to our blood, into our blood. So this is what it looks like. And then as we approach to the next time step, right, we have 1 minus K of the previous concentration that has been metabolized. So you can kind of imagine this, right? I'm just going to draw two diagram. So we have, for example, CT. For example, we can kind of envision this, right? We have T plus 1 over here, right? That's the time. And the concentration, right? Realistically, what it should do is it should go down. And the reason it goes down is because our body is metabolizing the drug, right? So what we have is there should be a decrease in concentration, and it actually decreased by a factor of 1 minus K times our previous concentration, right? Our previous concentration times our, the amount of concentration of drug that still exists, which is 1 minus K. So we will have CT plus 1, okay? Right, so we can start and construct an equation which goes like this. So CT plus 1, concentration on the next time frame is going to be equal to the CT, which is the concentration of the current, times our 1 minus K, which is how much of the previous concentration is still left. And you just multiply by 1 minus K. And then you want to, in addition, add A. Because as we see here, every time we go to a new time frame, A amount of concentration has been added. And therefore, we have a formula like this. So first of all, we have the original, right? And then concentration. And then we will say is decayed. And we also have A, which is our new injection. So this is the answer for part A. CT plus 1 equals to CT times 1 minus K plus A. Now, I'm going to tell you what I done wrong for part A. So I originally write CT plus 1 equals to CT 1 minus K plus A times 1 minus k. So my thought process was, okay, totally understand that because original concentration, the decay. But you see here, we also add A, so shouldn't A also undergoes that decaying process, right? Let me just hide it again. This decaying process of 1 minus k throughout the time frame. That was my process, right? Shouldn't A undergoes the decaying as well? Now, what I didn't notice is that A is actually already counted within our CT, because CT itself is the total accumulated concentration. So A itself is already included, right? Just by looking at CT here, right? You have this one adding A. So A itself is already included within the total concentration. So you don't have to additionally decay it again. Does that make sense? Because it already exists within CT. Imagine if this is CT, right? Then A is already here. Then you don't need to additionally add A and additionally 1 minus K. The CT has already been factored in with the decaying constant, right? The 1 minus K. We don't need to additionally decay the A again. And so that's how I originally kind of messed it up, but that's okay. You know, you can learn from all these examples, and I'm an undergrad student as well. I'm in the process of learning. So part B, unfortunately, for this video, I'm not going to plot the graph with you because it takes quite some time and a long process. And I found that kind of self-explanatory. I can do one example so we can kind of follow through what's going on. So we're just writing back the equations, CT plus 1 equals to CT times 1 minus K plus A. So what the question told us is C naught is 120, C naught is 120, A is 80, and K is 1 over 2. So right off the bat, what we can do is you can start by substitutioning, right? So with C naught, we have the initial one. So we can find C1 equals to C naught times 1 minus K plus A. And just by substitution, we can find that 120, 1 minus K, K is 1 over 2, and 1 minus 1 over 2 is 1 over 2. So 1 over 2 plus 80. And therefore, we're going to have 120 divided by 2 is 60. 60 plus 80 is 140. And we can try it for C2 as well. For C2, we have C naught, well, C1, right, times 1 minus K plus A equals to 140 divided by 2 plus 80. Then we have 70 plus 80. We would have 150. And so on and so forth. And we can even continue trying. So let's say we have C3, right? With C3, we have C2, 1 minus K plus A. And then we're going to have C2 is 150 times 1 over 2 plus 80. 150 divided by 2 is 75. 75 plus 80, we have 155. Okay, so if you continue on, you can actually find something interesting. So 140 to 150, right? It's a big jump. It's like a plus 10. But then 150 to 155 is plus 5. So we can kind of see, actually, if you plot it, we can see a graph that could go something like this. Okay, if you plot it. And of course, don't forget that this is continuous, by the way. It looks continuous, which is actually wrong. It should be a discrete function, so it should go something like this. Dot, 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 dot. So it's 1, 2, 3, 4, 5. Right, for t. This is a discrete function, discrete time model. So make sure that we kind of look something like this, not like this. But, you know, they both have the same trajectory, per se. And that's your answer. So I hope you enjoyed this video, and stay tuned for more.